Out there in the silent velvet dark lies an abyss so profound it defies all human scales of distance and time. It is an arena of unimaginable violence and serene beauty, where stellar metropolises glitter against an endless backdrop of nothing. For most of our history, we gazed upon this celestial ocean and saw permanence and eternal and unchanging clockwork. This grand assumption, comforting in its stability, was wrong, utterly and magnificently wrong. The cosmos is alive with a deep and secret motion, not the familiar waltz of planets or the slow spin of galaxies, but a far more fundamental movement woven into reality itself. The very fabric of space-time is stretching, carrying everything with it on an inexorable outward journey. This was the first great revolution in our cosmic understanding, a revelation that our home is not a static stage but a swelling, unfurling narrative whose beginning we could finally glimpse. Edwin Hubble, in the 1920 seconds, was the architect of this paradigm shift. Through the lens of the world's most powerful telescopes, he found that the great spiral nebulae were not clouds within our own Milky Way. They were island universes adrift in the void, each a city of billions of suns. His meticulous observations revealed something even more startling. These distant stellar assemblies were all rushing away from us. The farther a galaxy was, the faster it appeared to recede. This wasn't a chaotic explosion, but an elegant, orderly process. Imagine a loaf of raisin bread rising in an oven. From the perspective of any single raisin, all the other raisins are moving away, and the more distant ones move away faster. No raisin is at the center. The expansion is happening everywhere at once. Our existence is embedded in this rising dough of space-time. Hubble's discovery transformed our perception of everything. It meant the universe had a history, a dynamic past. If things are moving apart now, then long ago they must have been impossibly close together, born from a singular, fiery instant. The Big Bang was no longer a wild speculation, it was a necessity. For decades, this new story was guided by a familiar character: gravity. The immense gravitational pull of all the matter in the cosmos, both the shining stars and the unseen dark matter, should act as a brake. This cosmic leash, woven from the combined mass of trillions of galaxies, was expected to be slowing the expansion down. The great question became a matter of destiny. Would the swelling of space-time eventually halt and reverse, leading to a catastrophic big crunch? Or would it slow forever, never quite stopping, fading into a cold eternity? The fate of reality hinged on this cosmic tug-of-war between the outward momentum of the Big Bang and gravity's inward pull. To find the answer, astronomers needed to build a time machine. Their vessel would not be made of metal and wires, but of light itself, the ancient photons that have traversed the vastness of space for billions of years. By looking deep into the cosmos, we look back in time. The challenge was finding a standard candle, a celestial beacon, with a known reliable brightness visible across cosmic epochs. If you know how bright a light truly is, you can judge its distance by how dim it appears. The solution was found in the spectacular death of a certain type of star. A type Ia supernova is a thermonuclear cataclysm of stunning proportions. It occurs when a white dwarf, the dense corpse of a sun-like star, siphons material from a companion until it reaches a critical mass. At that precise point, it ignites in a runaway fusion reaction, obliterating itself in a blaze of glory that can outshine an entire galaxy. Because they all trigger at this same critical mass, they all achieve a nearly identical peak luminosity. They are the universe's most perfect standard candles. In the late 1990 seconds, two competing teams of scientists embarked on a monumental quest to map the history of cosmic expansion. They would hunt for these distant, ghostly supernovas to measure the universe's expansion rate in the distant past. Their goal was to quantify the deceleration to finally see the fingerprints of gravity slowing down the cosmic journey. With painstaking effort, they gathered their data, pointing their instruments at the faintest smudges in the deepest fields of view. The numbers trickled in, were cross-checked and analyzed, and they made no sense. The distant supernovas, the ones that showed us the universe of the past, were dimmer than they should have been. They were farther away than any existing model could explain. This was not a small error or a subtle deviation. It was a profound and shocking contradiction. The only way for these stellar explosions to be so unexpectedly far was if the expansion of the universe was not slowing down. In the last 5 to 6 billion years, it has been speeding up. Something was pushing spacetime apart, overpowering the collective gravity of all the matter in existence. The foot was not on the brake, it was on the accelerator. The discovery was so outlandish, so contrary to all expectation, that the research team spent months searching for their own mistakes. Perhaps intergalactic dust was obscuring the light. Maybe the supernovas of the past were intrinsically different. Every alternative explanation was investigated and one by one ruled out. The conclusion became inescapable. The cosmos is in the grip of a mysterious, repulsive influence. A strange energy inherent to the vacuum of space itself was driving the galaxies apart at an ever-increasing rate. They called it dark energy. This name is not a statement of deep understanding, but an admission of profound ignorance. It is dark because it does not interact with light. It is completely invisible. It is energy because it is the only thing in physics that could produce a repulsive anti-gravitational effect on such a grand scale. Its presence solves the mystery of the accelerating expansion, but it opens a chasm of even deeper questions. What is this phantom essence? Where does it come from? The simplest and most accepted explanation was a concept first proposed and later discarded by Albert Einstein. He called it the cosmological constant, a fudge factor in his equations of general relativity that would allow for a static universe. When Hubble proved the universe was not static, Einstein called it his biggest blunder. Yet in a stunning reversal, this blunder was resurrected as the most likely candidate for the cosmic accelerator. In this view, the repulsive force is a constant, unchanging property of space. As more space comes into existence through expansion, more of this energy appears, creating an unstoppable feedback loop. The more the cosmos swells, the more dominant the phantom force becomes. This conception of reality became the foundation of the standard model of cosmology, known as Lambda-CDM. Lambda, the Greek letter, represents the cosmological constant. CDM stands for cold dark matter, the unseen scaffolding upon which galaxies are built. This framework has been astonishingly successful for over 2 decades. It accurately predicts the large-scale structure of the cosmos, the distribution of galactic clusters, and the faint afterglow of the Big Bang, the cosmic microwave background radiation. The model painted a clear, if unsettling, picture of our ultimate destiny. A universe dominated by a constant, unyielding, repulsive agent is fated to a future of chilling isolation. The acceleration would continue forever, pushing galaxies apart so fast that eventually the light from even our nearest neighbors would be unable to reach us. The sky would slowly empty, leaving our own Milky Way, an isolated island in an endless, unobservable void. Stars would eventually burn out, matter would decay, and the whole of creation would descend into a state of maximum entropy. A cold, dark, and featureless eternity known as the heat death or big freeze. This was the accepted fate, the logical endpoint of our best observations. Until now, science is never settled. It is a relentless process of questioning, of pushing instruments to their limits and scrutinizing data for the slightest crack in the edifice of our understanding. For years, cosmologists have been building new tools, enormous surveys designed to map the universe with a breadth and precision previously unimaginable. Projects like the Dark Energy Survey have charted the positions and distances of hundreds of millions of galaxies. Researchers have refined their measurements of those crucial supernovas, creating vast new catalogues that probe cosmic history in high definition. And within this deluge of new information, tantalizing hints have emerged, whispers of a deviation, a sign that the Great Repeller might not be so constant after all. The new evidence is subtle, buried deep within statistical analyses of immense datasets. It comes from combining multiple ways of measuring the cosmos. One method still uses our standard candles, the type Ia supernovas, but now with far greater numbers and accuracy than the original discovery. Another technique relies on something called baryon acoustic oscillations. These are the faint, frozen echoes of sound waves that rippled through the hot, dense plasma of the very early universe. These primordial ripples created a preference for galaxies to form at a specific standard distance from each other. This distance, about 500 million light-years today, acts as a standard ruler. By observing how large this ruler appears at different cosmic eras, investigators can map the expansion history of spacetime. When scientists combine the latest supernova data with this standard ruler and other cosmic clues, they found a curious discrepancy. The established Lambda-CDM model, with its unchanging cosmological constant, still fits the data well, but not perfectly. A different kind of model, one where the mysterious repulsive influence changes over time, seems to fit the observations slightly better. Specifically, the data hints that the phantom essence might be dynamic. It might not be a constant property of the vacuum. Instead, it could be a field, something that can change, evolve, and decay. This evolving field has a name: quintessence. The analysis points to a possibility that is both thrilling and profound. The data suggests that this cosmic repulsive agent may have been stronger in the past and has recently shown signs of weakening. It is as if the engine driving the universe's acceleration is sputtering, its power output beginning to fade. The term dying is a dramatic one, and it is crucial to state that this evidence is not yet definitive. The statistical significance is still at a level where it could be a fluke, a subtle error in our measurements, or a misunderstanding of our instruments. But it is a thread, a loose strand in the cosmic tapestry that physicists are pulling on with intense curiosity. If this indication holds up, it represents the first major crack in the standard model of cosmology in a generation. It would mean our universe's past was more complex, and its future far more uncertain than we ever imagined. If the invisible influence is indeed waning, what does that mean for our destiny? The lonely, frozen fate of the heat death is no longer a certainty. A new set of possibilities, some even more dramatic, enters the stage. Imagine the cosmic tug-of-war once more. For billions of years, the phantom force has been winning, stretching reality apart. But if its strength is now diminishing, the balance of power could shift. Gravity, patient and relentless, might begin to regain the upper hand. The cosmic acceleration would first slow to a halt. Then, ever so slowly, the direction of motion could reverse. The universe would stop expanding and begin to contract. This would be the beginning of the Big Crunch. Across billions of years, galaxies would cease their retreat and start a long journey back toward each other. The cosmic microwave background, currently a frigid 2.7 Kelvin, would begin to heat up as its photons are blue-shifted by the contraction. Eventually, the sky would glow brighter than the surface of the sun. Galactic clusters would merge, then individual stellar islands would collide. Stars would be ripped apart, and the universe would devolve back into a primordial plasma, then into a soup of elementary particles. Finally, in a cataclysmic implosion, the entire fabric of spacetime would collapse back into the singularity from which it came. A fiery and spectacular end, the precise opposite of its beginning. This vision of a collapsing cosmos opens the door to an even more tantalizing idea, a cyclical universe. What if the Big Crunch is not an ending but a transition? Some theoretical frameworks propose a big bounce. In this scenario, as the universe collapses, quantum gravitational effects, which are not yet understood, would intervene at the last moment. They would prevent the singularity from forming and cause reality to rebound, triggering a new Big Bang and a new cosmos. Our existence could be just one chapter in an infinite cycle of expansion and contraction, of death and rebirth. An eternal cosmic phoenix, forever rising from its own ashes. It's a breathtakingly grand and elegant concept, one that solves the thorny problem of what came before the Big Bang. There was no before, there was only the previous cycle. This potential for a renewed, gravitationally dominated future stands in stark contrast to another theoretical fate, the Big Rip. This violent end was considered possible if dark energy were to times strengthen, times over time. Such a phantom energy would become so powerful it would eventually overcome not just the gravity between galaxies but all other forces. It would tear galactic clusters apart, then unbind the Milky Way itself. Solar systems would be dismantled, planets would explode, and finally, the very atoms that make up our bodies would be ripped asunder. The new evidence, however, points away from this terrifying scenario and towards a gentler, or at least more cyclical destiny. We stand at a pivotal moment in the history of science. We have found a hint, a clue that the fundamental story of our cosmos might need a radical revision, but a hint is not a proof. The scientific community is now charged with an urgent task to test this extraordinary claim with extraordinary evidence. The next decade will be a golden age for cosmology, with a new generation of observatories poised to map the heavens with astonishing fidelity. The Vera C. Rubin Observatory, perched high in the Chilean Andes, will survey the entire visible sky every few nights. It will discover thousands of new Type Ia supernovas, creating a map of cosmic expansion with unprecedented detail. The Euclid Space Telescope, a European mission now soaring through space, is designed specifically to investigate the nature of the phantom essence. It will measure the shapes and positions of billions of galaxies, charting the influence of both dark matter and the cosmic repulsive agent throughout 10 billion years of cosmic history. These instruments and others like them are our tools for a cross-examination. They will either confirm that the Great Repeller is indeed fading, launching a revolution in physics, or they will show the current anomaly to be a phantom of statistics, reaffirming the standard model. Whatever the answer, the quest itself changes us. It forces us to confront the sheer scale of reality and our place within it. We live on a fragile mote of dust, orbiting an unremarkable star in an ordinary galaxy among trillions. Yet from this humble vantage point, through the power of reason, curiosity, and collaboration, we can chart the history of everything. We can weigh the universe, determine its age, and now we are asking about its ultimate fate. The fact that we can even pose the question is a testament to the remarkable potential of the human mind. The cosmos, once perceived as a silent, unchanging backdrop, is now revealed as a dynamic and evolving entity. Its grand narrative is still being written, and we have just read a new, unexpected sentence. The possibility that the dominant force in our universe is not constant, that it is a dynamic character in the cosmic story, is transformative. It suggests a more complex, more interconnected reality where the vacuum of space is not empty but thrumming with a life of its own. The fate of everything from the dance of galaxies to the persistence of matter hangs on the true nature of this invisible influence. So we look up at the night sky no longer with a sense of static eternity, but with a new sense of suspense. We are living through a profound shift in understanding. The story we have told ourselves for the last quarter century about a universe accelerating into lonely oblivion may be wrong. The final chapter has not yet been written. Is reality destined for fire or for ice? For a final singular collapse or an endless cyclical rebirth? The data from our telescopes holds the clues. And out there in the silent velvet dark, the universe is waiting to tell us its secrets.